Hello there, welcome to the intermediate tutorials about the sound basics. In these tutorials we're going to discuss some of the same subject as in the beginner tutorials, but we will extend them a bit more, plus we're going to see some new subjects. Let's start with the speed of sound. Earlier in the beginner tutorial we discussed on how we can calculate the speed of sound based on the temperature of the medium that carries it. However, that is derived from a more complex formula. So as you can see in the following formula, C equals to velocity, K is the elastic bulk modulus, and the Greek R is the density. So the speed of sound depends to the square root of the analogy of the elastic bulk modulus, which is actually a factor that measures the resistance of the medium to compress under a given amount of some external pressure, to the density of the medium. Also, the speed of sound is affected by the speed of the medium that carries it. The simplest example for this is the wind. If the wind has the same direction as the sound, it will add speed. If it has the opposite direction, it will reduce the speed. Finally, there is a phenomenon known as acoustic shadow. Sounds weird, doesn't it? An acoustic shadow can be created from a sound source at some distance because the sound is actually refracted upwards. That's due to the fact that the temperature is decreasing as the altitude is increased for the first 11 kilometers above the surface of the Earth. That is happening because the temperature and the altitude are inversely proportional. And as the sound is moving away from the surface of Earth and consequently from us, the listeners, it creates an acoustic shadow. This can also be called as the negative speed gradient, and the opposite effect is called positive speed gradient. However, where do we meet the positive speed gradient? It might sound weird, but the positive speed gradient effect is observed in the stratosphere, which is 20 kilometers above the surface of the Earth. That's due to the ozone layer that creates an increase in the temperature. Earlier in the beginner tutorials we discussed about the sound waves. Now we're going to get a bit deeper in their sound propagation. So as a sound wave is traveling through the medium at a specific distance from the sound source, the properties of the medium vary in time. Properties such as pressure, velocity and displacement, and that's actually very normal because the energy that is transferred through the particles forces them to change their properties in a constant basis. At the same time, if we pick a moment in time, their properties will vary in space. It's the exact opposite. As the energy is transferred from the sound source to the receiver at the same moment, all the particles in the space will have different values for the properties mentioned before. Now, these waves are called longitudinal and are present in gases, liquids and solids. However, for the solids, the sound is also transferred as transverse waves. As we mentioned before, the longitudinal waves are using compressions and refractions to travel. The transverse waves are using an alternate shear stress in a relative angle to the direction of the propagation. Also, make a side note that if you ever happen to be in space, you won't be able to hear anything, and that's only because the sound cannot travel through the vacuum.